So in this video, what I wanted to do is to talk about this integral of sine of kx over x. We're going to integrate from 0 to infinity. This is an improper integral for two reasons. One is that sine of x over x is not well defined at 0, so you have to be a little careful there, even though that's a removable discontinuity. And you have an improper integral again because this is the limit is x goes to infinity. So so this is an improper integral for two reasons. I had originally planned to talk about sine of kx over x, where k is some real number. If k is 0, this integral is 0. If k is negative, we're going to do one thing, which I'll describe at the end. If k is positive, we're going to do something else. So I'm just going to handle one particular value of k, and that'll just be k equals 1. And then this entire process will work with whatever positive value of k you want there. What we're going to do is we're going to look at the integral. We're going to look at the integral of e to the iz over z dz, and then we'll take imaginary parts. We're going to integrate over gamma, where gamma is the following contour. Now, a lot of the art of contour integration comes to figuring out what are the right contours that you want to integrate over. And here we already have e to the iz, and so what we're going to do is we're going to integrate over a rectangle. Now we have to be a little bit careful here because we're going to have a singularity at 0, and we'll have to deal with that and figure out, how to handle that. So what we're going to do is we're going to integrate over a rectangle. Okay, so we're going to integrate over this rectangle. Let's say this goes from negative r to r on the real axis. And then we're going to have to try and connect the rectangle, but we're going to have a slight problem at 0. And so to fix that, we're going to have to do this indented contour and travel along a circle of radius, say epsilon, all the way back. And so this is the orientation. It's positively oriented, as you would expect. Okay, and so let's say that this value here is epsilon and then negative epsilon. So that's just some piece of the circle of radius epsilon centered at the origin. Now, the entire integral over gamma is really easy to evaluate because it's 0. All the poles are outside the contour. So we don't really need to do anything here as far as evaluating the entire integral. But what I'm going to do is I'm going to break this up into 6 pieces. So we'll have C1, C2, C3, C4, and C5. And then C6 is going to be this little circle here. And in fact, instead of calling it C6, let me call it C sub epsilon. Okay, so C sub epsilon is this piece. That's, again, oriented. It's going to be a circle of radius epsilon, but it's going to be oriented backwards to the way we're used to because we're traveling, in this case, clockwise to keep the entire curve positively oriented, the entire contour. So that's it. That's the contour that we're going to use that turns out to be very useful. We're going to think of this integral over gamma. So the integral over gamma is going to be the integral over gamma 1 plus the integral over gamma 2. This is bad shorthand, but hopefully this gets the idea across. We're just going to integrate over all of these separately. The integral of gamma 5 plus the integral over the last piece, which is gamma epsilon. And it turns out that gamma 1, gamma 2, gamma 3 are all going to tend to 0 as r goes to 0. So I should actually be a little bit more careful here. Gamma is going to depend on r. And so what we're going to have to do to evaluate this limit is think about this integral. So we're going to think about this integral as, let me add a little bit of room here, but we're going to think about this as the limit as r goes to infinity of the integral from, I'm not writing this very well, but there's the integral from epsilon to r sine of x over x. And then we're also going to take the limit as epsilon goes to 0. Okay, and so that's how we're going to think about this integral. Okay, so as r goes to infinity and as epsilon goes to 0. Okay. And if we want to specify 0 from the right, it doesn't matter. So there we are. So that's what we're going to do. And then, like I said, we're going to look at this integral e to the iz over z over this contour gamma. And it turns out that this integral that we're going to look at, it's easier to think about this integral in terms of what's called the Cauchy principal value. And so I don't want to get into principal value. I think I've probably even mentioned it once or twice in the course before, but what it turns out what's going to be easier is actually not to calculate the integral from 0 to infinity, but to calculate the integral from negative infinity to infinity. And so if I look at this integral from negative infinity to infinity of sine of x over x, and I compare it to the integral from 0 to infinity, sine of x and x are both odd, so the ratio is an even function, and therefore we can just take 1/2 of the integral from negative infinity to infinity, and that'll give us the integral that we're looking for. Okay, so at a certain point, we're going to have to take 1/2 of our answer, and that's to account for the fact that we're really only integrating from 0 to infinity. All right, and I think we're almost there. So now our job is to calculate this integral over gamma. We're going to get some value, and then our integral that we're looking for, so the integral from negative infinity to infinity of sine of x over x dx is going to turn out to be the limit as r goes to infinity, as epsilon goes to 0, of the integral over gamma 4 plus the integral over gamma 5. Okay, so we're going to have to think about what those are. We'll calculate those, and then that'll give us our value that we're looking for. And then if we can solve all the other integrals, then we can solve for the value that we're looking for based on the other terms. Okay, so that's our strategy. So, all right, so let's think about first, what's the limit as r goes to infinity of the integral over gamma 1 plus the integral over gamma 2 plus the integral over gamma 3. So remember that that's this piece. I don't know why I called them C1 up here and gamma 1 down there. Sorry. When I say C1, I mean gamma. I'm being slightly inconsistent here. That's fine. It should be pretty clear what I mean. But let me just change all the C's to gammas, and that'll make me happier. So gamma 1, gamma 2, gamma 3. All right. So what we're going to do first is think about what's the integral over gamma 1, gamma 2, and gamma 3 as r goes to 0. And it turns out that this integral is not going to be equal to r, but as r goes to infinity, these will all be 0. And so I'm just going to evaluate one of them, and the others will be completely analogous. But let's just look at the integral over gamma 1. So let's look at the limit as r goes to infinity of the integral over gamma 1. And again, we're integrating e to the iz over z dz. Okay. Now, let's think about how this is going to go. We're going to have, let's see. So gamma 1 is going to be given by the curve. So gamma 1 of t is going to be given by our x value is always r. And then our imaginary part is going to go from 0 to r. So let's just call it r plus I t, where t goes from 0 to r. So that's all we have to do to parameterize that curve. And then the integral over gamma 1. So now the integral over gamma 1 is going to be equal to the following. It's going to be the integral from 0 to r. We're going to have e to the I of gamma. So that's r plus it over gamma, r plus it, times gamma prime. That's going to be times I. Yeah, that's it. So I dt. Okay, and so now we need to think about what's going to happen with this integral. And notice that the exponential term e to the I z, if z is complex, then that's going to decay to 0 very quickly if you have a large imaginary part. So just to be more precise, what I mean is that if we take this exponent and just distribute, we're going to have the integral from 0 to r of e to the I r, which is going to be some point on the unit circle. It's bounded, it's nice, it doesn't matter, times e to the minus t, all over r plus I t dt. And now this integral is going to be very hard to evaluate, but what's going to turn out to be the case here is that we can think about this as, we can just basically use the same result that we were doing before. This is going to be less than or equal to the limit of, let's see, what's the maximum value of the modulus here? So it's going to be the maximum where t is in gamma 1 of the modulus of e to the IR, e to the minus t, r plus it, times the length of the curve, which is r. Okay, and so here to say t is in gamma 1 means that t goes from 0 to r. Okay, because that's the range of our t values. And think about what's happening here. What you have is you have e to the IR. Now r is some real number, so e to the IR, the modulus is just 1. And then you have an exponential term, e to the IT, over a linear term. Okay, and what's going to happen here is that this limit, this exponential is going to win, and you're going to get that this limit, as r goes to infinity, this limit is going to be 0. Okay, so anyways, so to make a long story short, this limit's going to turn out to be 0 because this exponential term is going to go faster to 0 than anything else. So that is the deal there, and that's how that works. If you wanted to do this super formally, what you could do is you could look at the function e to the negative t over r plus it. And in fact, you could take the modulus, turn this into a function with real coefficients, do the calc1 thing, find the maximum, and it'll turn out to be e to the minus r with some constants in front. And so if you have an e to the minus r times r, that's going to go to 0 by L'Hopital's rule. Anyways, I'll let you fill in the details, but that's how that works. And that's just gamma 1. Gamma 2 and gamma 3 are going to be similar. Okay, so it turns out that those limits go to 0 as the size of this rectangle gets bigger and bigger. Okay, so the bigger the rectangle, this limit's going to tend to 0. All right. So we already said that the limit of the integral over gamma 1, gamma 2, and gamma 3 go to 0. The integral over gamma 4 and gamma 5 are exactly the values that we're looking for. That's going to give us our limit. So all that's left to do is to calculate the limit over gamma sub e. Now gamma sub e, I'm going to write this. Gamma sub e of t is going to be, it's going to be the circle centered at 0 of radius epsilon, but traversed counterclockwise. So this is going to be epsilon times e to the minus it, again, where t goes from 0 to, t is going to go from 0 to pi. So that's that. And if we calculate this integral, so if you calculate the integral over gamma e, even though the residue is outside, we can't quite use the residue theorem. But if you apply the Laurent series expansion for our function, you're going to turn, it turns out that what's going to happen, e to the iz over z dz, as epsilon goes to 0, is that this is going to be 2 pi I times the residue of this function, e to the iz over z, at 0. And the residue of e to the iz over z is going to be, I'm sorry, not 2 pi I apologize, just pi I. The reason why it's pi I is that we're not integrating over the entire circle, we're integrating over a circle of, well, over a piece of a circle with arc length pi. So actually it's the arc length that goes there. So if you were to integrate, say from the north pole of a circle all the way over to the right side, you would get pi over 2I times the residue. Whatever the arc length is, you would get, if that's alpha, then your integral would be alpha I times the residue. So in our case, we got pi I times the residue. This is not a trivial fact here, but I'm not going to prove it. So if you just write out the Laurent series expansion, it turns out all you need to know is the residue. And then the residue of e to the iz over z is going to be 1 as z goes to 0. Because what you do is you multiply by z, that cancels with the z there, and then plug in z equals 0, you get 1. So this is pi times I. So to put everything together, what we know is that the integral over gamma 1 plus gamma 2 plus gamma 3 plus the integral over gamma 4 plus the integral over gamma 5 plus the integral over gamma epsilon, as r goes to infinity, is going to be 0. And on the other hand, as r goes to infinity, I mean, this limit is going to be 0 for all r. So in particular, as r goes to infinity, we'll get 0. And if we take the limit of each of these integrals, we're going to end up with the limit of gamma 1, gamma 2, gamma 3, so that'll be 0, plus the limit of gamma 4 plus gamma 5. This is going to be the limit as r goes to infinity of the integral over gamma 4, plus the integral over gamma 5, plus the limit as r goes to infinity and as epsilon goes to 0 of the integral over gamma e. Okay, and so this tells us that 0 is equal to the integral that we're after. Okay, so that's the integral. So this is going to be the integral from negative infinity to infinity of sine of x over x. Well, let me be a little bit more precise here. Yeah, just to be a little bit more precise here, let's just get to the punchline. So the integral from negative infinity to infinity of sine x over x, and we're going to take half of that to get the integral. Let's just call the integral that we're looking for I. So we're going to take half of that because, again, we only wanted the integral from 0 to infinity, and this is an even function. But this is going to turn out to be the imaginary part of the integral over gamma, which turned out to be, I'm sorry, the integral over gamma e. And the reason why it's negative is that this is going to be the integral that we want. This is the piece that we have. Okay, so that's pi I. And I'm sorry, I missed, let's see, did I miss anything? Yeah, I know, I see our mistake here, my mistake, not your mistake, my mistake. I forgot to account for the fact that this integral is negatively oriented. So this is actually minus pi I. Now everything works out. So this is going to be 1/2 of the imaginary part of minus pi I being pi over 2. Okay, so the integral, I screwed up some of the details there, but I think you can put all the pieces together. This integral is going to be gamma, is going to be pi over 2. Now, I do want to say just 30 seconds more. If we were to evaluate the integral from 0 to infinity of sine of minus x over x, 2 tricks. One is that you can just factor the negative out of sine because it's an odd function. Everything's fine. You get negative pi over 2. That's really all you need. Or if you wanted to, you could integrate over this indented rectangle. So you would go this way, this way, this way. You'd still have to avoid the origin for the reasons that we did before. And then the argument would be basically just completely analogous to what we did before. I think it's easier just to think about bringing out the negative because sine is an odd function, but there you go. Okay, so again, another real integral that we can evaluate using residue calculus.